Good day, everyone. So we are now back here again on chapter 4, KJM 442 heat and fluid. So in this part, we'll be covering air conditioning. So this is part 2B. In part 2A, we have covered the Dalton's law and the energy conservation law to analyze problems related to atmospheric air. So here in part 2B, for air conditioning, we will be focusing mostly on psychrometric chart. What is a psychrometric chart? How to use a psychrometric chart to solve problems in air conditioning. Okay, so we will now begin with our next part, which is the psychrometric chart. So as you can see here, we have the psychrometric chart shown almost like a shoe design, right? We will see how it looks like, right? So for a given fixed total air vapor pressure, the properties of the mixture are given in graphical form on a psychrometric chart. So you can see that the state of the atmospheric air at a specified pressure is completely specified by two independent intensive properties. So you can have any of these two properties. You can use that to specify the condition of the specified pressure or the air properties that you have. The rest of the properties can be calculated easily from the previous relations, right? So you've done that in the previous sections. The sizing of a typical air conditioning system involves numerous such calculations, which may eventually be very cumbersome for most of the engineers, right? So in order to avoid that, so there is a clear motivation to computerize calculations or to do these calculations once and to present the data in the form of easily readable charts. So such charts, we call them as psychrometric chart, right? So you can actually represent the air conditioning processes on a psychrometric chart easily. So let's say this is your reference point. If you want to move towards cooling, so this reference point will then move towards the left as shown here. So if you have a reference point here again, if you want to do a heating in terms of air conditioning processes, then this point will move towards the right as shown here. For humidifying, it will move towards up. For dehumidifying, it will move towards down. So it becomes a very valuable aid in visualizing the air conditioning processes. You can also do the cooling and dehumidifying, where the direction of movement will be towards this direction, and heating and humidifying will move in this direction, right? So there are many parameters that you can obtain. You can have the dry bulb temperature, you can have wet bulb temperature, you can have the enthalpy lines, you can have the specific volume line, you can have the specific humidity property obtained from the psychrometric chart, right? You can also have the relative humidity line. So the actual psychrometric chart looks like what is going to be presented in our next slide. So this is the psychrometric chart. This is how it looks like. So I would like to bring your attention to the first important term here. If you want to use this psychrometric chart, you must make sure that your pressure is 101.325 kilopascal. Any pressure besides this pressure, you will not be able to use the psychrometric chart. 100 kilopascal is not 101.325 kilopascal. For 100 kilopascal, you will have no choice but to use the earlier equations. But if your pressure is at 1 atm or 101.325 kilopascal, then you can freely use the psychrometric chart to solve problems related to air conditioning processes. So as you can see from here, you have the psychrometric chart shown as what we've discussed earlier in a shoe form. All right, so on the y-axis here, you have all the values for humidity ratio. So this humidity ratio, bear in mind, the unit is in grams moisture per kilogram dry air. We mostly use values in kilograms moisture per kilogram dry air. But in this chart, the value for humidity ratio is given as grams moisture per kilogram dry air. So if you read 22, So the value is 22 grams moisture per kilogram dry air. So you will need to convert this into kilogram moisture per kilogram dry air for your further calculations. So that is the value that you have on your y-axis here. On your x-axis, you have dry bulb temperature in degrees C. So you have 0, 10, 20, 30, 40, and 50. You have your wet bulb temperature shown here on the dotted lines here, right? So these are the wet bulb temperatures. So this is the wet bulb temperature at 30 degrees C. So as you go down, this is the wet bulb temperature is 25 degrees C. Wet bulb temperature of 15 degrees C is shown here. 10 degrees C is shown here. 5 degrees C is shown here, and so on. Then you also have lines representing your relative humidity. So this is the line representing 10% relative humidity. You have 20% relative humidity, 30, 40, 50, 60, 70, 80, 90. And the last line here represents the relative humidity of 100%. So saturation is also known as relative humidity of 100%. Right? So you also have saturation temperature given here. The other property that you can get from psychrometric chart is your specific volume. So those lines are represented by this darkened line here. So you have 0.94. As you go down, it reduces to 0.92. This is 0.91, 0.94, 0.93, 0.92, 0.91, 0.90, and so on. All right, so those are the lines for specific volume, and you will see that the unit is volume cubic meter per kilogram, meter cube per kilogram of dry air. So you can also find the enthalpy, so based on the scale given here. Right, so these are the parameters that you can actually obtain from a psychrometric chart. And remember, again, we can only use the psychrometric chart when the pressure is 101.325. Nothing more, nothing less than this. Anything more than this or anything less than this value, you will need to use the formulas as what we've discussed earlier. So right, so even 100 kilopascal, you cannot use the psychrometric chart. It has to be 101.325 kilopascal or 1 atm. So now let's look at this question here. So you have how to use psychrometric chart. So we will then learn how to use the psychrometric chart based on this question. So you have dry and wet bulb temperature of atmospheric air at 1 atm. This is very important. So the moment they say is 1 atm or 101.325 kilopascal, you know automatically you can use the psychrometric chart. So the pressure are measured with sling psychrometer and determined to be 25 degrees C and 15 degrees C respectively. So you have dry bulb temperature 25, wet bulb temperature 15. So these are the two parameters given. So in the psychrometric chart, you have more than two parameters. So in order to find other parameters, you need a minimum of two parameters. So those two parameters are given to you, right? So based on these two parameters, how are you going to use the psychrometric chart to find specific humidity, relative humidity, and enthalpy of the air for this problem? So now let's look at the solution. So this is the psychrometric chart. Now remember, based on the question, you are given 25 degrees C as the dry bulb temperature, 15 degrees C as the wet bulb temperature, and the pressure is given as 101.325, which corresponds to this, and we are very confident that we can use psychrometric chart because the pressure corresponds to the pressure that is stated here. So now let's start. So we have the dry bulb temperature 25 degrees C. So you can see here, this is the axis for the dry bulb temperature. So you need to find where is 25 degrees C. So we have 20 degrees C here. We have 30 degrees C here. Obviously 25 degrees C is somewhere in between. So what you need to do is you need to draw a line. All right, so draw a line at 25 degrees C to represent this value. So this is the line that I've drawn to represent the value for 25 degrees C. Now we need to find what is the wet bulb temperature. So the wet bulb temperature line is shown here, the dotted lines. So we have 30 degrees C here, we have 25 degrees C here, but we need to find where is the 15 degrees C. So if you find the 15 degrees C, the 15 degrees C line for wet bulb temperature is shown here. So it is inclined as the dotted lines here. So again we draw another line there. So based on these two parameters, you will find an intersection point here. So this intersection point is very important because based on this intersection point, we will find the other parameters that we want. So the first parameter that we are looking for is the specific humidity. So the specific humidity is given here. Right, so this is the specific humidity. What you need to do is from this intersection point, you need to extrapolate a straight line that intersects with this axis in order to obtain your humidity ratio. So you draw a line, so it intersects at this point, you read what is the value here, and that becomes your specific humidity value, right? So the next point that we want to find is your enthalpy. So enthalpy, you draw a line which is parallel to these lines and it intersects to this point here. Based on the scale given, then you can find what is the enthalpy that you want. And next is you want to find your relative humidity. To find relative humidity, it is between 30% to 40%. Now you've got to estimate, draw a line which is parallel to these two lines, all right? So this is the blue line that I've drawn. So this is parallel, and then you estimate between 30 to 40 here on your appropriate scales that you can find, what is the value of this line. So it seems like it is between 33 and 34%. All right, so then you can use the psychometric chart here as what we've discussed to solve the problem that is given to you. All right, so I hope it helps. The illustration helps you to find the values. Now let's look at another example. So this is again based on psychometric chart. So this is a room. Again, the most important parameter if you want to know whether you can use the psychometric chart or not is the pressure. So the pressure here is at 1 atm, so we can use the psychometric chart easily. So we need two parameters in order to use the psychometric chart. So what is given to you is the dry bulb temperature at 35 and the relative humidity is given to you at 40%. So use the psychometric chart to find these 5 parameters: specific humidity, enthalpy, wet bulb temperature, dew point temperature, and the specific volume of the air. Now let's look how to find that. So we have our psychometric chart. So we want to now find where is our temperature at 35 degrees C. So dry bulb temperature is given here. So 35 degrees C, we draw a line straight up, vertical line at 35 degrees C. So that is to represent our dry bulb temperature. Then we find what is our relative humidity, 40%. So we have, these are the relative humidity lines. So 10% is here, 20, 30, 40. So this is the line that represents 40% relative humidity. So that will give you an intersection point here. So that is your intersection point as shown as the blue dot there. Now based on this, we want to find what is our specific humidity. So to do that, from this intersection point, you pull a line straight horizontally so that you cut this axis, y-axis, to find the value of your specific humidity. So wherever you find the intersection here, so based on the scale given here, you find out what is the value. That will be the value of your specific humidity. Next, to find the enthalpy, we draw a line again parallel to these lines until we intersect this scale here, and then the value at this particular point based on the scale given to you, that will be the enthalpy of that problem. Now to find wet bulb temperature, we need to draw a line parallel to the wet bulb lines here. So to do that, so first we will find the dew point temperature again. To find the dew point temperature, all you need to do is you draw a straight line, horizontal line, until it intersects to the saturation temperature line here. So the line that cuts the scale here will give you the dew point temperature. All right, so you can find the dew point temperature based on that. And then this is your specific volume of the air, specific volume of the air, you see that these are the lines that represents the specific volume of the air. So you can use the specific volume of the air based on this 0.92, and then you have 0.91, 0.90, and then here we have 0.89. So between 0.89 and 0.90 you can divide the scales and find out what is your specific volume of the air. Now remember, we have not found the wet bulb temperature line. So the wet bulb temperature line is the same as the enthalpy line that we have drawn earlier, right? So you can estimate what is your wet bulb temperature. You see that this is your wet bulb temperature that you have here, which is 25, and here is 20, and then there is an increment of 1. So this line here is on the wet bulb temperature of this line. So you will see that your wet bulb temperature is 24 degrees Celsius. So with that, you are able to find all the 5 parameters that you need to solve the problems for problem 6.7. Right? So hope the illustration helps you. So find all the values on your own, learn how to use the psychometric chart. Right, so it is very important for you to know how to find the values based on psychometric chart, because it will be very helpful for you in the exams and also for your assignments later on, and not forgetting your time. Right, so that was on your psychometric chart. So now we have air conditioning processes. So again, just to recap, air conditioning processes include simple heating. So when you heat up something, you raise the temperature. Simple cooling is just by lowering the temperature. Humidifying is where you add the moisture. Dehumidifying is removing moisture. So these are the typical air conditioning processes that you have. Sometimes you can combine 1, 2 or more of these processes, right, to bring the air to the desired temperature and humidity level. Sometimes you need to have heating with humidifying. Sometimes you need to have cooling with dehumidifying. So you can combine these processes together. So these are the various air conditioning processes as what we have discussed earlier. So cooling, heating, humidifying, dehumidifying, or you can combine them, cooling and dehumidifying, heating and humidifying. Now let's look at one of the simple heating and cooling processes. So for simple heating and cooling processes, you will notice your specific humidity is always constant, right? So we have many residential heating systems consist of a stove, a heat pump, or an electric resistance heater. So this is your heater or heating coil. The air in this system is heated by circulating it through a duct that contains the tubing for the hot gases or electric resistance wire. Now, if you want to do cooling, you can do the same setup, but instead of having heat here, you can then pass the air over some coils through which a refrigerant or chilled water flows, right? So heating and cooling appears as a horizontal line since no moisture is added or removed from the air. So this statement, you can refer to the psychometric chart here. For an example, if you want to cool the stream of air from 30 degrees Celsius to 12 degrees Celsius, you will see that the line moves in a horizontal direction because you are not humidifying or dehumidifying anything. So it will move from point 1 to point 2. Because there is a change in temperature, your relative humidity values will also change. But since the line is moving in a horizontal direction, your specific humidity value is not changing, and that is why your omega is constant, right? So the formulas that we have here: dry air mass, so conservation of mass, right? The mass that is moving in the first position is equal to the mass that is going into the second position, which is the total mass, right? So since it's a horizontal line on a psychometric chart, your specific humidity will not change, and then because you are either adding heat or removing heat, your enthalpies will change, and based on that enthalpy change, you can then find out your energy balance. All right, so these are the formulas that you can have for simple heating and cooling, and you can also illustrate it easily on a psychometric chart here. All right, then you have heating with humidification. So now heating is just heating. So what you have, a stream of air coming from point 1, which is exposed to heating coils. So it will then heat up. As a result of that, your temperature will rise. So for an example here, we have 0.1 to 0.2. So 0.1 is 10 degrees Celsius. You want to heat it up to 22 degrees Celsius. So then you will pass this stream of air through some heating coil. As a result of that, your temperature will raise up to 22. As from 0.1 to 0.2, you are not adding any moisture or removing any moisture. So as a result of that, this line is horizontal. So, and due to that, your omega remains same. So omega 1 is equals to omega 2. So this happens at the heating section. Now, because we have heating with humidification here means you are adding moisture. So you can either spray some water vapor into the system as shown here with the help of a humidifier. So when your air moves from 0.2, this is heated, and then it goes to 0.3, you are adding moisture. So when you add moisture, your specific humidity changes and the line on the psychometric chart moves in this direction. So it goes from 0.2 to 0.3, and you will see that there is an increase in your specific humidity from this level to this level. So, and that is the reason why you have omega 3 more than omega 2 here. And these are the formulas that you use for dry air mass balance. You will see that the conservation of mass balance is applied here. The amount of mass that you have 0.1 is conserved at 0.2 and is also conserved at 0.3. So the total mass of air is conserved, so they remain the same. Now, if you want to find the water mass balance, we will see that the amount of water that is available at 0.1 and amount of water that is available, water moisture in the air available at 0.2 is same. So that results in omega 1 equals to omega 2. So energy balance at 0.1 and 0.2 is given by this formula again. So this is for the heating section. Now, since we are having a humidifier, this humidifier is adding some water moisture into the air, and that is given by this formula. So amount of air at 0.2 times with omega 2, that gives you this relationship, plus with the amount of water vapor that are being introduced by the humidifier equals to this m dot A3 times omega 3. So if you want to know how much water vapor is being introduced by the humidifier, you can rearrange this, and that will give you m dot A omega 3 minus omega 2. And this will give you the amount of water moisture that is being injected into the air conditioning process. So that is for heating and humidification. We also have the next part, which is the cooling with dehumidification. In cooling with dehumidification, as you can see here, we are reducing the temperature. So when you reduce the temperature, right, so again the 0.1 moves towards the left of the psychometric chart until your relative humidity becomes 100%, or the air reaches very high humidity that it becomes saturated. So the other meaning for saturated level is humidity is at 100%. So you can see here specific humidity of air remains constant during a simple cooling process. You can see here specific humidity is constant, right? But its relative humidity increases. So from 80% it has increased to 100%. If the relative humidity reaches undesirably high levels, it may be necessary to remove some moisture from the air. That is to dehumidify it, and this is what happens in our air conditioning processes. All right, so this requires cooling the air below its dew point temperature. So again, the dry air mass balance is same, right? Water mass balance, because you are losing water, so we want to know how much water is dehumidified, the condensate removal. You can use this formula to calculate, right? And then the energy balance is given by this formula. You can calculate out how much heat is removed from the cooling section of these cooling coils by using m dot h1 minus h2, which are the enthalpy differences between 0.1 and 0.2, And remember, you must also minus from the vapor that we are losing through the condensate removal. So that will be the equation used for the energy balance for cooling with dehumidification. Right. So now we can look at sample problem 6.8. So here we have a heating section consists of a 38 cm diameter duct that houses a 4 kilowatt electrical resistance heater. The air enters the heating section at 1 atm, again 1 atm, you can use psychometric chart, 10 degrees Celsius and 40% relative humidity at a velocity of 8 meters per second. So determine the exit temperature, exit relative humidity of the air and the exit velocity. So this is the skeleton again. So we use these assumptions. This is a steady flow process, and thus the mass flow rate of dry air remains constant throughout the entire process. So the mass from point 1 to point 2 is the same. Dry air and water vapor are considered as ideal gases. Kinetic and potential energy changes are negligible. Right. So for the analysis, the amount of moisture in the air remains constant. Right. So omega 1 is equals to omega 2 as it flows through the heating. So this is only heating, no humidification, no dehumidification. Right. Inlet state of air is completely specified and we have 1 atm. So you can use your psychometric chart. So go to point number 1. Point number 1, you have 10 degrees C dry bulb temperature, 40% relative humidity. Based on these two parameters, find what is your H1, omega 1 and specific volume. Right. So this can be obtained from your psychometric chart, and note that omega 1 is equals to omega 2. Then you can find your mass flow rate. So m dot is equals to rho AV. So based on the formula. So this is 1 over specific volume is your rho. All right. Make sure you know that. And your volume, you can calculate out your volume. I'm sorry, this is not volume, this is your velocity. So 8 meters per second is your velocity. And then this is your cross-sectional area. So make sure you know how to calculate your cross-sectional area for a 38 cm diameter, pi d squared over 4, but make sure you change cm to meter as well. So that will give you the mass flow rate in kilogram per second. So Q in is given to you. Q in is 4 kilowatt. All right. So H1 is known. So m dot A is known from here. So you should be able to find what is your H2 easily. So now you have your omega 2. All right. You have your H2. So again, 2 points are given for point number 2. And then go back to your psychometric chart. Find what is your dry bulb temperature at T2, relative humidity, and specific volume. All right. So once you've got that, the exit velocity again based on your mass flow rate. So this is your volume flow rate divided by specific volume should be equal to your volume flow rate at 0.2 divided by specific volume. So you rearrange it into this formula, find your V2 based on this formula, and that will give you the exit velocity. Right. So the skeleton is given to you. You should be able to solve this problem easily, find out the values here. All right. So if there are any problems, we will discuss it in the class. So now we have another problem. So you have air that enters a 40 cm diameter cooling section. Now you have a cooling section at 1 atm again, 32 degrees C and 30% relative humidity at a velocity of 18 meters per second. Heat is removed from the air at a rate of 1200 kilojoule per minute. You are asked to determine the exit temperature, exit relative humidity of the air, and the exit velocity. So let's see how to do this. So again, assumptions are same as the previous example. So m dot A1 equals to m dot A2 equals to m dot A. So because it's only single duct, so the mass flow rate is considered to be the same for both the points. And then the amount of moisture remains same because it's a simple cooling. So omega 1 equals to omega 2. All right. So no humidification, no dehumidification. So the inlet state is given 32 degrees C and 30% relative humidity. So this is given to you at 0.1. So based on 0.1 parameters, 32 degrees C dry bulb temperature, 30% relative humidity, go to your psychrometric chart, find what is your H1, omega 1 and specific volume. So omega 1 equals to your omega 2. So similarly, you can also find your mass flow rate, rho AV. So rho is 1 over V1, which is your specific volume here. Velocity is given to you as 18. And your cross-sectional area can be found using this diameter, 40 cm diameter. Right? Change this to meter. Don't forget that. And then from the energy balance, you can see that negative Q out equals to m dot A H2 minus H1. So negative because you are absorbing the heat out. So you have the quantity negative here. All right. So this is given to you in kilojoule per minute. We need to change this to SI. So we will then change this to kilojoule per second by dividing this with 60. So that is how you change kilojoule per minute to kilojoule per second, because 1 minute is 60 seconds. So you divide this with 60, that will give you negative 1/200 divided by 60. Why negative? Because for cooling you are absorbing the heat out of the system. All right. So m dot A is given here. All right. H1 is known. Negative Q out is here. So you can find H2. So now for point number 2, you have H2. You have omega 2, which is similar to omega 1. So once you have these 2 points, you should be able to find what is T2, relative humidity at point number 2, and specific volume at point number 2. And then to find your velocity, we use back the same formula as discussed earlier. Should be able to get what is the velocity at point number 2. So give it a try, find the values, and you should be able to get all the values needed. All right, as explained in this presentation. Now we have the third example, sample problem 6.10. So again, you have air at 1 atm, 15 degrees C, 60% relative humidity. You are given a rate, volumetric rate, 2 meter cube per minute. Is first heated to 20 degrees C in a heating section and then humidified by introducing water vapor. The air leaves the humidifying section at 25 degrees C and 65% relative humidity. You are asked to determine the amount of steam added to the air and the amount of heat transferred to the air in the heating section. Now let's look at the skeleton of the solution here. So assumptions again, because it's a single duct, so your mass flow rate, conservation of mass is conserved, right? And then you have inlet conditions given to you, dry bulb temperature 15, relative humidity 60. So based on that, you should be able to find what is your H1 and omega 1. You are also given the exit conditions. So the exit conditions, dry bulb temperature is 25 and your relative humidity is 65. Now based on this, based on the exit conditions after the heating coil, right? So that is given to you. So you should be able to find what is your H3 and omega 3, right? So H3 and omega 3 are found based on this temperature and this relative humidity. So you have these 2 points, go to your psychrometric chart, and that will give you your H3 and omega 3, right? So based on that, you will have all these values that you need, right? To find H2 is quite easy. Omega 1 is known, which is equals to your omega 2. And you also know that the temperature of dry bulb temperature is 20 degrees C at 0.2. So use this temperature and use this omega, and you should be able to find what is your H2, right? So amount of moisture in the air remains constant as it flows from the heating section. From here to here, omega is same, right? But your omega changes from 0.2 to 0.3. So you have omega 3 and your omega 2. Find the difference in these two. So that will be the amount of steam added to the air in the heating section. So the delta omega, the difference between omega 3 and omega 2, is the amount of steam added to the air, right? And then to find the heat transfer, it is nothing but H2 minus H1. Right, so that is the heat transfer through the heating coil, and you find that heat transfer to the air in the heating section per unit mass of air is given as H2 minus H1. That will give you the answer in kilojoule per kilogram dry. So give it a try, get the values, skeleton is there, it should be easy. You should be able to get all the values that you need. So practice this. Another problem, we have air that enters a window air conditioner at 1 atm, 32 degrees C and 70% relative humidity at a rate of 2 meter cube per minute, and it leaves as saturated air as at 15 degrees C. Part of the moisture in the air that condenses during the process is also removed at 15 degrees C. So you are asked to determine the rates of heat and moisture removal from the air. So this is the skeleton again. So this is cooling with dehumidification. All right. So conservation of mass. So the inlet and exit states are given. So this is the inlet. So based on 32 dry bulb temperature, relative humidity 70%. So find what is your H1, omega 1 and specific volume from your psychometric chart. Exit conditions are also given, T2 and relative humidity 2, 15 degrees. Now this is saturated. So if it's saturated, the value for your relative humidity will be found right towards the edge of the psychometric chart, the last line for the relative humidity after 90%. So that will give you your H2 and omega 2. All right. So you must also find your enthalpy. All right. So liquid, saturated liquid at 15 degrees C, right? Because this condenses at 15 degrees C. So you must find saturated liquid at 15 degrees C from table A4. So find what is the enthalpy for that. And then this will give you, because you don't know what is the mass flow rate, but you are given a volume flow rate. So your volume flow rate divided by specific volume, which we have found from here, that will give you the mass flow rate that you want. Right, so with that you'll be able to find the mass flow rate. And now based on this equation, energy balance, you will be able to find what is the mass of condensate removal from the system. So omega 1 minus omega 2 times with the mass flow rate of the air, that will give you the water mass balance, amount of water that condenses out from the system. And the Q out, amount of heat that is absorbed by the cooling coils, is given by this formula again, right? M dot A H1 minus H2 minus the heat loss through the condensate removal. So this is the condensate removal, M dot W, which is found from here, and HW is this value that you found from table A4, and that will give you your Q out. All right, so please try this question. And the last one that we have here is your adiabatic mixing of air streams. So in many air conditioning applications, we have two different streams mixing in the adiabatic sections of the what do you call that mixing section as shown here. So you can have the return air from the confined space of the room coming in, and this is mixed with fresh air coming from the outside. Because in very large buildings or most production and process plants and hospitals, we require that the conditioned air to be mixed with certain fraction of fresh air outside. So you have two ducts. One is carrying the return air from the room, and this is mixed with the outside fresh air in this mixing section. So once they are mixed, and then they are delivered again to the desired confined space, like in the hospital room or office building. So again, based on the mass balance, again, if you have mass coming in from 0.1, total mass from 0.2, if you add it up, that should be the total mass that is going in at 0.3. So for water vapor, again, so we will use this mass balance, and for the energy, again, it is shown as this mass balance here. All right, so on the psychometric chart, you can see that you have 0.1 and 0.2 here. So what it does is from 0.1, right? So this is cooled air coming in, and this is the fresh air at a higher temperature, and they are mixed, and you will get this particular property at point number 3. right? So based on this relationship that is shown here, you can then find out your ratio of mass flow rate of uh, air coming in at 0.1 divided by mass flow rate of air coming in from 0.2. You can find the specific humidity or 0.3 based on the values that you've got at 0.1 and 0.2, and you can equate this and you should be able to get your specific humidity at 0.3, and you can also equate this enthalpy relationship to this value here, the ratio, and you should be able to get what is the enthalpy at H3. Right, so this is for adiabatic mixing of air streams. Okay, so that is the end of our part 2, chapter 4, refrigeration and air conditioning. So hopefully you have learned on what is a refrigeration, the importance of refrigeration cycle, the difference between refrigerator and heat pump, all the associated calculations based on TS diagram for ideal vapor compression cycles, refrigeration cycles, and not forgetting the important formulas that you need to use to analyze problems related to atmospheric air, and also the use of psychometric chart to solve problems related to air conditioning. Thank you.